The concrete designed for our highways, bridges, and other structures is intended to be of the highest quality. It should consist of approved materials that are correctly proportioned and mixed, and then carefully transported to the job and placed. In practice, however, the concrete ordered for the job may not be the concrete that's actually placed. At critical points during production, transport, or handling on site, the concrete's quality may be jeopardized. Batcher mixer slips are not always a guarantee that you have the right concrete in the truck. For example, if wash water was left in the truck before it was loaded, the mix may be too wet. Or the truck driver may decide to add water if the mix begins to stiffen. So it's important and it's required that the quality of the concrete be verified before the concrete is cast. Verification is provided by conventional controlled tests performed in the field. This presentation is the first of 4 videotapes on quality control of concrete on site. Here in Part 1 and in Part 2 are presented the conventional control tests for determining concrete quality at the job site. In Parts 3 and 4, you'll see new quality control procedures that have been developed by Sharp and others for testing concrete both before and after it's cast. So, here in Part 1, we'll look at sampling concrete and at the test methods for temperature and slump. In Part 2, we'll look at the test methods for air content and unit weight, as well as the procedures for making cylinders and beams. Our first topic then is sampling. Before any of the tests can be performed, a sample of the concrete is needed, a representative sample. The concrete to be tested has to be typical of the entire truckload. Sampling should be done according to AASHTO designation T141. The basic rule is this: don't take the sample from the beginning or end of the discharge. Take it from the first 1/3 of the discharge, but never from the first 2 cubic feet. To obtain the sample, either the entire stream should be caught in a container, or the chute should be swung over to the side. The important point is to get the entire stream. Cutting the stream in half, like this, is unacceptable. The rim of the bucket will knock some of the large aggregate out of the sample. The sample should be mixed with a shovel just until it has a uniform appearance. Then it should be covered to protect it from the sun and the wind. Samples must not be allowed to dry out. One last point. Testing must be completed within 15 minutes after obtaining the sample. Now, temperature. The temperature of fresh concrete affects the rate at which concrete gains strength, the amount of strength the concrete ultimately acquires, and the porosity of the concrete. Checking concrete temperature is simple. It should be done according to ASTM C1064. All that's needed is a standard thermometer, such as an ASTM liquid in glass type, or a metal immersion type. The thermometer is inserted into the fresh sample so that the temperature sensing portion is submerged at least 3 inches. The concrete should be gently pressed around the thermometer so that the air temperature does not affect the reading. The thermometer is left in the concrete for 2 minutes or until the temperature stabilizes. Then the temperature is recorded. The measurement must be completed within 5 minutes after the sample is obtained. The temperature of in-place concrete is measured in the same way. Now, the air temperatures during concrete construction are also important. The high and low air temperatures must be monitored daily. Next on the list is the slump test, AASHTO T119. This is by far the oldest and most widely used test to measure the uniformity and consistency of concrete. Variations in slump generally indicate that changes have occurred in the properties or proportions of cement, aggregates, water, or admixtures. The equipment needed for slump tests includes a standard slump cone, a standard tamping rod, a scoop, a base, and a ruler or measuring tape. The slump cone should be reasonably clean, especially inside. The surfaces should be smooth, with no dried concrete on them. Also, there should be no major dents. A standard tamping rod is smooth with a rounded tip. Makeshift rods, such as cut-off reinforcing bar, are unacceptable. The base for the cone must be strong, rigid, and stable enough to support the tester as well as the concrete and equipment. It needs to be level and firmly supported so that it won't rock or bounce. The sample should be brought close to the test location and remixed if necessary until it looks uniform. The test is begun by first dampening the inside of the slump cone to keep the concrete from sticking to it. Then the base is dampened as well, so that it won't absorb water from the concrete. But no freestanding water should be left on the base. The cone should be set down on the base as close as possible to the sample. Next, the technician steps onto the footholds at the bottom of the cone and stays there. That's why the sample and cone need to be close to each other. The cone is filled by moving the scoop around the top to distribute the concrete as evenly as possible. The filling is done in 3 layers. Each layer should take up approximately 1/3 of the cone's volume. So the first layer should come up about 2.5 inches from the base. The second layer should come up about 6 inches. That's about halfway up the cone. And the third layer should overflow the cone. As each layer is placed in the cone, it's consolidated with a tamping rod. Starting at the perimeter, with its rounded tip downward, the rod is inclined slightly to match the slope of the cone. Otherwise, the concrete closest to the cone's sides will not be properly consolidated. The rodding should go to the bottom of this first layer, but just tap the base. Each layer is rodded 25 times, with about half of the strokes made near the perimeter. A spiraling pattern should be followed as the rod moves toward the center of the cone. The strokes are distributed uniformly. As the rod is moved away from the perimeter, it's returned to the vertical. The second layer fills about half of the cone's height. It's rotted the same as the first, with one difference. The rotting should just penetrate about a half inch into the first layer, not all the way down to the base. The third layer should overflow the cone. That way, the concrete stays above the cone throughout the rotting. If it drops below the top, the rotting should be stopped. More concrete should be added, and then the 25 spiraling strokes should be completed. And the rod should just penetrate the top of the second layer about 1/2 inch. With the cone full and the rotting completed, the surface of the concrete is struck off by moving the tamping rod across it in a screeding and rolling motion. The concrete surface must be level and fairly smooth. Next, any concrete that has spilled around the bottom of the cone must be removed. Otherwise, it may keep the sample from slumping properly when the cone is lifted off. However, the technician must be careful not to move the cone and disturb the concrete. Basically, both sides of the cone must be held still by pressure on either the handholds or footholds until the cone is removed. To remove the cone, both hands are placed on the handholds and downward pressure is applied to keep the cone stable before the feet are removed from the footholds. Now the cone is pulled straight up, slowly and steadily, without twisting or tilting. The removal should be completed in about 5 seconds. Slowly enough that the concrete doesn't pull on the cone. The cone is then set on the base, next to the concrete, without touching the concrete or jarring the base. Immediately, the tamping rod is laid flat across the top of the cone, extending over the concrete. A ruler or measuring tape is used to measure the distance between the bottom of the rod and the top of the concrete. The measurement should be made to a point that is directly above the center of the bottom of the concrete, not at the center of the top. The entire slump test must be accomplished within 2 minutes, as measured between the adding of the first layer and the measuring of the slump. And that's sampling, temperature, and slump. And the end of Part 1. In Part 2, we'll cover air content, unit weight, and the making of cylinders and beams.